Good afternoon, class. Today we're going to talk about Chapter 7. As always, please have your notes, your calculator, a periodic table, and a pen or pencil with you. Chapter 7 is all about chemical reactions and quantities. There are, in chemistry, many chemical reactions that we can possibly study. We use chemical equations to describe these chemical reactions. A chemical equation is just like a math equation or even a sentence in English. It tells you what's going on. In the case of the first example, you have two atoms of sodium in solid form reacting with two molecules of water in liquid form to form two sodium hydroxides dissolved in water plus one molecule of hydrogen gas. These numbers, the twos, outside of the atom or molecule tell you how many. In this case, two atoms of sodium, two molecules of water, two molecules of sodium hydroxide. The letters written in parentheses beside each atom or molecule tell you what state they're in. S for solid, L for liquid, G for gas, and the little AQ you see there stands for aqueous. A-Q-U-E-O-U-S, which means dissolved in water. Aqueous means dissolved in water. So again, all those little symbols tell you what state your chemicals are in. The numbers on the outside, called the prefixes, tell you how many. You may remember from before when we were talking about ionic and molecular compounds that the subscripts, like that little 2 there in the H2O, and the little 2 in the H2 tell you how many atoms of each kind of element are in one molecule. I.e., in one molecule of water, you have 2 hydrogens. In one molecule of H2 gas, you have 2 hydrogens. So those little subscripts down there tell you how many atoms you have within the molecule. Sometimes you may see other things, like for example this little triangle over this arrow. That tells you that you had to add heat in order to make the reaction go. Or you may also see a chemical compound written over the arrow, something like this. This tells you that it is a catalyst. Catalysts are written over the arrow because they're not used up in the reaction. All chemical equations must be balanced. This is because of the properties of conservation of matter. If you have 1 calcium on the left-hand side of the arrow, you must have 1 calcium on the right. If you have 3 oxygens on the left, you must have 3 oxygens on the right. You have 1 in this calcium oxide and 2 from the carbon dioxide. 1 carbon on the left, you must have 1 carbon on the right. So every element must be balanced. Let's take a look at some practice examples of this. In the first equation, you have aluminum and nitrate. Aluminum and nitrate, aluminum nitrate. You have 1 aluminum on the left, 1 aluminum. You have 3 nitrates on the left, 3 NO3s. You have 3 ammoniums, 3 NH4s, and 1 PO4. On the right-hand side, we have 1 aluminum, we have 1 NO3, we have, let's see here, 1 NH4, and we have 1 PO4. Now you will notice that when I wrote on the left and the right, I kept them in the same order, so I can see that I have 1 aluminum on the left, 1 aluminum on the right. 3 NO3s on the left, 1 on the right. 3 NH4s on the left, 1 on the right. 1 PO4 on the left, 1 on the right. If you write the ones on the right in a different order than you wrote the ones on the left, you could find yourself confused. Okay? So it is best to always write them in the same order. Okay, so again, let's take a look at what we got. Who is not balanced right now? who is out of whack. So we have 1 aluminum on the left, 1 aluminum on the right. 3 nitrates on the left, but only 1 on the right. 3 ammoniums on the left, only 1 on the right. And our PO4 is 1 and 1. So it's the 2 in the middle that are unbalanced. How can we fix that? Well, obviously, if we have more on the left than we have on the right, we need to increase the amounts on the right. We have 3 NO3 on the left, 1 on the right. Let's put a 3 here. We now have 3 NO3s and 3 NH4s. So we now have 1 aluminum on the left, 1 aluminum on the right, 3 nitrates on the left, 3 nitrates on the right, 3 ammonia on the left, 3 on the right, 1 PO4 on the left, 1 PO4 on the right. This equation is balanced. Let's take a look at the next example. On the next example, we have 1 silver on the left, 1 fluorine, 1 calcium, and 2 chlorine. On the right, we have 1 silver, 2 fluorine, 1 calcium, 1 chlorine. So as we can see, our silvers are balanced, our fluorines are not, our calciums are balanced, our chlorines are not. So it's fluorine and chlorine that we need to fix. We have 2 fluorine on the right, only 1 on the left. Since we have more on the right than we have on the left, it is the left we need to fix. So let's put a 2 here. That now gets us 2 fluorine. But it also changes the number of silvers that we had. We had 1, we now have 2. So we fixed one problem but created another problem for ourselves. Again, we now have 2 silver on the left, 1 silver on the right. Our calciums are still balanced, and our chlorines are out of whack. You have more on the left than you have on the right. You have 2 silver, 2 chlorine. You need 2 silver, 2 chlorine on the right. So let's add a 2 here. You now have 2 silver and 2 chlorine, and we are now balanced. Let's try another one. Let's look at the next one. We have 1 zinc on the left, 2 bromine, 1 lead, Pb, kind of a funny symbol for lead, and 2 nitrates. On the right, we have 1 zinc, we have 2 bromine, we have 1 lead, and 2 nitrates. This equation is already balanced. 1 zinc, 1 zinc. 2 bromine, 2 bromine, 1 lead, 2 nitrate, 2 nitrate. So we don't have to do anything to this equation to balance it. Okay, let's take a look at our next example. Next example. C2H4O2. So let's see here. We have 2 carbon, 4 hydrogen. We have 2 oxygen here, but we also have 2 oxygen here, both on the left side of the arrow. So we have 4 oxygen, 2 plus 2. On the right, we have 1 carbon, 2 hydrogen, and 2 oxygen here, plus 1 here for 3 oxygen. So our carbons are out of whack, our hydrogens are out of whack, and so are our oxygens. Where do we start? Well, you might notice that the oxygens are in the first molecule, the second molecule, the third molecule, and the fourth molecule. Since changing any one of those changes everything, I recommend leaving the oxygens alone for the moment. It's easier to start with either the carbon or the hydrogen, both of which appear in only one molecule on each side of the arrow. I don't think it matters which one you start with. Let's start with carbon since it's first on our list. You have 2 on the left, 1 on the right. Clearly we need to increase the right in order to match the left. Let's try adding a 2 here. So that now gets us to 2 carbon. However, that also changes our number of oxygen. We had 3, we now have 2 times 2 is 4, plus 1, we now have 5. Again, let's leave the oxygen alone until we fix both the carbon and the hydrogen. You have 4 hydrogen on the left, 2 hydrogen on the right. Clearly, we have more on the left than we have on the right. So let's add a 2 here to the right to increase our number of hydrogens. We've now changed our hydrogens from 2 to 4. 2 times 2 is 4. We have also again changed our number of hydrogens. We had 4, and now we have 4 plus 2 for a total of 6. So our carbons are fine, our oxygens are, our hydrogens, our carbons are fine, our hydrogens are fine. We just need to fix our oxygen. Looking at the left-hand side of the equation, you have oxygen in two different places. You have it as part of this molecule and this molecule. If we change the number in front of this molecule, we will also change the carbons and hydrogens, knocking us out of balance again. However, if we change the prefix in front of this molecule, we only change the oxygen. We currently have 4 oxygens, 2 from the first molecule, 2 from the second. If we add a 2 in front of the O2, we now have 2 times 2 is 4 plus 2 for a total of 6. Our equation is now in balance. 2 carbons on each side, 4 hydrogens, and 6 oxygens. This type of problem is something that requires practice, a lot of practice. I recommend you get your practice in on your homework, and if you need more assistance or want extra problems to practice with, please let me know. I'd be happy to give you some worksheets to look at. Oops, I just want to fix these 2's that we kind of erased a little bit. 2, okay. Let's look at the next one. 1 calcium, 1 copper, 2 fluorines. 1 calcium, 1 copper, 2 fluorines. Well, look at that. This one is already balanced. This one does not require any additional work on our part. Let's take a look at the next example. Okay, we have, an interesting combination here. So we have, let's skip the hydrogen here for a moment. We have 1 SO4, 1 sulfate. We have 1 boron, and now we have 3 hydrogens from the OH3 plus 2 here for a total of 5 hydrogens. And within this OH3, we have 3 oxygens that are not part of the sulfate. On the right-hand side, we have 3 SO4s, 2 borons, and we have 2 hydrogens, as well as 1 oxygen not part of the SO4. So 3 SO4 on the left, 1 on the right, 2 boron on the right, 1 on the left, 2 hydrogen on the left, 5 on the right. Nothing's in balance here. Absolutely nothing. Okay, where's the best place to start? Well, since we want to keep our sulfates together, our SO4s, and we don't want to change those up too much, let's try fixing that first. Let's put a 3 here. That gets us 3 SO4s. That also changes our hydrogens. We had 3 here and 3 and 6 here, right? 3 times 2. So 3 plus 6 is now 9 hydrogens. We still have 1 boron on the left, 2 on the right. We didn't change our loose oxygens that are not part of the SO4s. Let's try fixing our boron next. We have 1 on the left, 2 on the right. Let's put a 2 here. That fixes our borons. Now, that also changes our hydrogens. 2 times 3 is 6, plus 6. We now have 12 hydrogens. We've also changed our oxygens that are not part of the SO4. We have 3 OHs, right, and 2 BOH3s. So 2 times 3, we now have 6 oxygen. So sulfates, balanced, borons, balanced. Our hydrogen and our oxygen are out of whack. We have 12 hydrogen on the left, 2 on the right, 6 oxygen on the left, 1 on the right. Since on this side we have something that has just hydrogen and oxygen in it, let's change this. Because if we change the prefixes here, we're going to have to start all over again. It's going to mess up not just our oxygen, but our boron and our hydrogen. If you put a 6 in front of the water, you get 6 times 2 is 12 hydrogens, plus 6 times 1 is 6 oxygens. We now have 12 hydrogens, 6 oxygens, 6 oxygens. We're balanced. Again, this is something that requires a fair amount of practice. There should be practice problems in your textbook. practice problems on the homework, and if you still want some extra practice problems, please let me know. I'd be happy to give you some more. Okay. There are many different kinds of chemical reactions. Some of them are listed below. We have reactions that we call combination reactions. Combination reactions look a lot like what they sound. For instance, if you have H2 gas and you mix that with oxygen gas, you can get water in gas form, which we would call vapor. To balance this, of course, we would need a 2 here and a 2 here. Right? That gets us 4 hydrogens, 2 oxygens, 2 oxygens. Again, this is exactly what it sounds like. You have two things, right? An H2 and an O2, combining to make one thing. So a combination reaction sounds just like what it is. It's two things combining to make one thing. Decomposition reactions also sound like what they are. It is when you have one thing breaking down into multiple things. Okay? So we have on the right side potassium chloride and oxygen gas. So we have one thing breaking down into 2 or more things. This is a decomposition. Your chemical is decomposing. So they look like what the name sounds like. Single replacement reactions also look like what they sound like. It is when one thing is taking the place of something else. For example, if you have 2 silver molecules plus 2 molecules of hydrochloric acid, you get silver chloride, AgCl, plus hydrogen gas. Okay. Again, the silver is replacing the hydrogen to form silver chloride and hydrogen gas. So this sounds just like it is. It is a single replacement. One thing is replacing something else. Anybody care to guess what a double replacement looks like? A double replacement, just like a single replacement, is where two things are swapping spots. For example, if you have BaCl2, barium chloride, plus Na2SO4, sodium sulfate, they can swap spots to form barium sulfate and sodium chloride. So again, the barium and the sodium are swapping spots. So now you have barium sulfate and sodium chloride. This sounds just like its name. It's a double replacement reaction. Two things are swapping spots. Combustion reactions, you can't kind of really tell what they are just from the name. A combustion reaction is what happens when you have an organic compound, which is a compound containing carbon, hydrogen, and possibly oxygen or nitrogen, that is burning up in pure oxygen to form two products, carbon dioxide and water. So an example of this balanced is 2C8H8O3. This is your organic compound. It is burned in pure oxygen and it forms carbon dioxide and water. Now, in a combustion reaction, the products, right, the things that are produced on the right-hand side of the arrow, are always going to be carbon dioxide and water. These numbers here may change depending on the organic compound that you used, but the products are always carbon dioxide and water. The reactants, the things that are reacting together on the left-hand side of the arrow, are always going to be pure oxygen. And again, this number changes depending on what you need in order to balance this. And your organic compound, which is always a carbon and hydrogen compound, or a carbon, hydrogen, and oxygen compound, or carbon, hydrogen, oxygen, and nitrogen. Some reactions may fit into more than one reaction type. One of these types is called oxidation reduction, which is a subreaction. A single replacement reaction is also always an oxidation reduction reaction. In an oxidation reduction reaction, electrons are transferred from one substance to another. So in this example, A gives an electron to B. Therefore, A becomes more positive because it has lost some negativity, and B has gained an electron, it is reduced, and it becomes more negative. Example 2. The green patina on the Statue of Liberty is due to the oxidation of copper metal as it forms a green solid, copper oxide. In the following equation, who is oxidized and who is reduced? In the first example, we have two solid copper atoms. They are forming two copper ions, each one with a charge of +2, plus some number of electrons. Okay? Since the charges in this equation must be balanced, just like the atoms must be balanced, let's see what we have. We have two coppers, which have no charge, right? They're copper atoms. Remember that atoms are neutral. So on the left side of this equation, we have a 0, 2Cu with a 0. On the right-hand side, you have two coppers, each with a +2. So on the right-hand side of the arrow, we have 1, 2, 1, 2, for a total of 4 positives. 4 plus and 0 are not the same thing. So we need to add electrons, which have a negative charge, to make both sides equal. Well, how many negatives must you have to balance out the positives on the right-hand side of your equation? 4 positives, you must have 4 negatives. 4 positives plus 4 negatives gives you an overall charge of 0. 0 on the left, 0 on the right. They match. So those two coppers have lost a combined 4 electrons. Okay, they have lost 4 electrons. Let's look at the second half. We have oxygen gas, O2. Oops, oh, I forgot the plus electrons there. O2 plus some number. Oops, let's try that again. O2 plus some number of electrons gives you 2O2 with a 2 minus. Oxygen gas has no charge, as indicated by the molecule. There is no charge written in the upper right-hand corner, so we have a 0 on the left. On the right, we have two O2 minuses. So you have a 2 minus and a 2 minus. Right now, we have a 0 on the left and a -4 on the right. We need our charges to balance just like our atoms balance. We can only add electrons to make the charges balance, since we're dealing with a transfer of electrons. Electrons are negative. So we can only add negative charges either to the left or to the right. In order to make these two things equal to each other, if we add negatives to the left, 1, 2, 3, 4, we see that we can make these things balance. You have 4 negatives on the left, 4 negatives on the right. So oxygen has gained 4 electrons. In oxidation reduction reactions, the oxidation portion is the loss of electrons. Reduction is the gain. Oxidation is the loss. Reduction is the gain. There are 2 ways you can remember this. The first is the phrase oil rig. Oil rig stands for oxidation is loss. Reduction is gain. So oxidation is the loss of electrons, oil. Reduction is the gain of electrons, rig. If you don't like that phrase, there's another phrase you can use that will also help you remember this, and that is Leo the lion goes grr. I like this one. This is the one I learned in high school. Leo the lion goes grr stands for loses electrons oxidized, gains electrons reduce. So the element that loses electrons is the one that is oxidized, or is the oxidation half of the oxidation reduction pair. And the one that gains electrons is the one that is reduced, or the reduction half of an oxidation reduction reaction. In an oxidation reduction reaction, you always have one of each. So you can never have an oxidation-oxidation or a reduction-reduction. In this case, the copper is losing 4 electrons, sorry. So it is oxidized. It is the oxidation half. Oxygen is gaining those 4 electrons. Therefore, oxygen is reduced, and this is the reduction half of the equation. Example 3. Identify each of the following as oxidation or reduction and determine the electrons transferred. So we have tin in solid form going to form an ion with a 4 plus charge plus some number of electrons. Again, we need our charges to balance. We have a 0 on the left and 4 pluses on the right. How many minuses must we add to make these two things equal to each other? 1, 2, 3, 4. Now you can see that our charges are balanced. We have a 0 on the left and a 0 on the right. So we need 4 electrons here. So tin has gone from a 0 to a 4 plus, and in the process it has lost 4 electrons. Therefore, is this an oxidation or a reduction? Remember oil rig or Leo goes grr. Since we are losing electrons, this is an oxidation. All right, let's look at the next one. We have Fe3 plus some number of electrons going to form Fe plus 2. So right now we have 3 pluses on the left, 2 pluses on the right. Remember that we need them to be equal to each other. Not necessarily 0, but equal to each other. How many minuses must I add on the left to make this happen? Well, I have 2 pluses on the right, 3 on the left. Let's add 1 minus. That 1 minus and 1 of the pluses cancel, and you are left with overall 2 pluses on the left, 2 pluses on the right. So this is Fe3 plus 1 electron gives you Fe2 plus. Therefore, the iron has gained an electron. If we remember our phrases, oil rig and Leo goes grr, we can say that since the iron has gained an electron, that is reduced. This is the reduction half of the equation. Let's look at another one. We have Cl2 gas goes Cl2 minus. So on the left we have a 0. On the right we have 2 minuses. We must make these two things equal to each other. Again, not necessarily 0, but equal to each other. And we are doing that by adding electrons to the left or the right. So where would I put those electrons to get these two things to match? Well, if I put the 2 electrons on the left, okay, then we can see that we have 2 minus on the left, 2 minus on the right. So chlorine has gained 2 electrons. Therefore, is it oxidized or reduced? Well, if it has gained 2 electrons, the chlorine has been reduced, and this is a reduction equation. Let's try another one. We have 2 Ag plus going to make 2 silver solids, and we have 2 Cl minuses going to Cl2. So let's see what we do about electrons. On the top equation we have 2 pluses on the left and a 0 on the right. Where are we going to put our minuses to make these two things equal to each other? What about if we put 2 minuses here? Then our 2 minuses and our 2 pluses cancel each other out, and we have a 0 on the left and a 0 on the right. So let's put our 2 electrons in here. What about the bottom equation? We have 2 Cl minuses, which is 2 negative charges, and we have a Cl2 with no charge, so this is 0. So again, where are we going to add our electrons to make these two things equal to each other? Well, let's add them on the right. We have 1. We can see that we now match. We have a -2 on the left, -2 on the right. So let's go ahead and put those 2 electrons in. Okay. Now remember I said this is an oxidation reduction reaction. You must always have both an oxidation and a reduction. On the top half, the silver is gaining 2 electrons. Gaining 2 electrons. Therefore, it is reduced. The chlorine is losing 2 electrons. Therefore, it is oxidized. Okay, so again, a little bit more about oxidation and reduction. Oxidation is the loss of electrons, as we said. Reduction is the gain of electrons. But oxidation can also mean the addition of oxygen or the loss of hydrogen. Reduction can also mean the loss of oxygen or the gain of hydrogen. For example, the biochemical molecule FAD, which stands for flavin adenine dinucleotide, can be reduced to FADH2 by the transfer of 2 hydrogen atoms. Transfer of 2 hydrogen atoms. So we have gained hydrogen, therefore we are reducing the molecule. In many biochemical oxidation reduction reactions which happen in your body, the transfer of hydrogen atoms is necessary for the production of energy. Also, for example, the body metabolizes methyl alcohol, which is a poisonous substance, by the following reaction. CH3OH, methanol, reduces or decomposes to formaldehyde, oxidizes, decomposes to formaldehyde and 2H. Then the H2CO further combines with oxygen to form formic acid. This is oxidation, the addition of O atoms. Then the formic acid reacts further with more oxygen to form carbon dioxide and water. The intermediate products, including formaldehyde, are toxic, causing headaches and possible death because they interfere with key reactions in cells. The particular definition of oxidation and reduction that you use depends on the process that occurs in the reaction. Oxidation always involves the loss of electrons, but could also be the addition of oxygen and/or the loss of hydrogen. Reduction always involves a gain of electrons, but could also be the loss of oxygen or the gain of hydrogen. This concludes Chapter 7, Part 1. Thank you for listening.